All right, great, thank you. Hi, everybody. Good to be here. So my name is Kara Schechtman, and I'll be presenting on our work, Discretion in the Loop, Human Expertise in Algorithm-Assisted College Advising. This is joint work with our wonderful authors, advising authors at Georgia State, Benjamin Brandon and Jenise Stafford, as well as the co-principal investigators on this work, Hannah Lee and Lydia Liu. So to provide a little bit of background, so our setting is the use of early warning systems in college advising. So college advising, this is when students who are already enrolled in college come to dedicated advisors who give them advice about things like courses and enrollment and majors, these kinds of things. And early warning systems are predictive algorithms that aim to try to forecast for students based on their prior academic data, whether they might experience adverse educational outcomes, so things like dropping out or poor grades, and then flag those students to advisors for additional assistance so advisors can take action to help those students. So much prior academic work on early warning systems tends to focus on the quality of algorithmic predictions. And this is important, of course, that our predictions be high quality, but it is only one part of the puzzle when it comes to actually improving student outcomes. We also need to look at whether the use of these algorithmic systems actually do drive better outcomes for students. And on this front, there has been less work, but there is some evidence through randomized trials where some advisors are provisioned these decision aids and some are not, that these algorithms or use of these algorithmic systems can actually positively affect student outcomes. What our work focuses on is kind of a middle stage, which is the role of the advisor in actually driving these positive outcomes. So if you think about an advisor who gets an alert that a student might be struggling, what do they need to do in order to actually help that student? Presumably, it's not only looking at the algorithmic prediction, but it's also incorporating a lot of other information in order to decide what action to take to actually help that student. So for example, they might want to have a conversation with the student. They might incorporate things like institutional context, and they might also draw on their prior experience. So this stage of how the advisor actually takes discretionary action based on an algorithmic prediction to support students, there's not much work on this. And education researchers point to this as an important part of the process that a lot of education tech research tends to overlook. So this is where we focus our attention. We want to understand how do advisors discretionarily use these tools to drive impact. And that gives some sort of theoretical motivation for why we're interested in this, but there's also a practical motivation of scaling. So if we want to take something that looks like a promising educational intervention of flagging students and scale that up to, say, a whole university from just a randomized trial, it'll be really important for us to understand if advisors' actions are playing an important role in the impacts of that system and how. Because while algorithmic predictions can maybe scale up pretty arbitrarily, advisor actions face capacity constraints. If you try to scale up, say, the number of students that an advisor is assigned, they might not have the time to talk to all those students and learn the information that they need in order to assist them and use the tool to drive positive impact. So this motivates our research question, which is how do we test for human expertise in algorithm-assisted decision-making in settings where actions, like the advisor's actions, affect outcomes? And this is a question that we look at in the context of college advising, but it also will apply to any setting where there's sort of this discretionary layer that acts as a bridge between an algorithmic system and an outcome. So you could think of something like treatment decisions by a doctor in a medical context, for example. And to answer this question, we do two things. So first, we devise a causal framework to formalize this question of drawing on human expertise to improve outcomes. And then second, we use that to guide a mixed method study of a real algorithmic decision aid at Georgia State's University. Okay, so to start with the causal framework and formalizing the decision-making scenario. So we use structural causal models to model the decision-making scenario, and I'll walk through the creation of this causal model part by part. So let's say we have an advisor who is taking some action, and the goal of that action is to improve student outcomes, like, say, their grades. In making that decision, as we saw before, the advisor draws on both algorithmic predictions and also on non-algorithmic context. So things like their conversations with students where they might learn details about students' interests and personalities. We represent the algorithmically available data through this variable xt, which is just the data available to any algorithm. So we can view an algorithm as a compression of that data. And the non-algorithmic context we represent through this variable ut. And the arrows here are mean cause. So like the advisor action is caused by looking at this data and considering their context. And we only consider action or data and non-algorithmic context that actually bear signal about the outcome. So if something is irrelevant to student outcomes, like just say what mood the advisor was in that day, our model exogenizes that kind of information. And given this sort of causal setting, our goal is to say, when is an advisor's action expertly targeted? And expertly targeted here means sort of like discretionarily improving outcomes. And we divide that into 3 causal criteria, which I just informally gloss on this slide. The formal definitions are in the paper. The first is that the action that the advisor takes needs to actually improve the student's outcome. The second needs to be that the action was targeted using non-algorithmic information about the student, so say something they learned in an advising meeting, not from the data available to the algorithm. And third is that the outcome was heterogeneous in that non-algorithmic context. So the idea here is that we want the action to actually improve because the advisor noticed something that was important to driving that outcome and then targeted the action because the student's non-algorithmic context made it so that they would respond well to that action. So this is kind of gives us a definition, but now there's the question of how can we actually identify this from data? So in many sort of quantitative studies or settings where we have access to a data set, we won't actually have access to the non-algorithmic context. This is because non-algorithmic context oftentimes is stuff in the long tail. It's stuff that's hard to encode in sort of a tabular fashion because it can be very rare situations or very sort of abstract concepts. So we assume that we have access to outcomes, actions, and algorithmically available data. And we show in the paper that expertly targeted action can't be identified from observational data about these 3 things alone. However, we can look for a necessary condition of expertly targeted action, which is this conditional independence condition, which was proposed for use in predictive contexts, so contexts where you're not actually trying to affect the outcome, but trying to forecast the outcome. And in our setting, it's a necessary condition of this targeting. And the condition is conditional dependence of actions and outcomes given all the data available to an algorithm. And we borrowed the test from Allure et al. To test for this conditional independence statement, and I'll sort of gloss it because I think it gives an intuition for why this might suggest non-algorithmic information. So it's basically a permutation test where you take students who look like they are identical to the algorithm. You generate fake data sets by swapping the actions that advisors took for those students. And then you see if in those fake data sets, actions are less predictive of student outcomes. And if so, that suggests that maybe there was some signal, potentially signal that was non-algorithmic context the advisor was drawing on that made actions more predictive of those outcomes in the true data set. So this can give us a sign, although it's not sufficient for expertly targeted action, that expertly targeted action was present. Okay, so with that test, we actually apply this test to real data from a treatment arm of a randomized trial of an algorithmic decision aid. The trial was of an advising protocol where advisors drew on real-time and early alerts, so that's the early warning system. And the data set includes student baseline characteristics, so that's our algorithmically available data, advisor interventions, so that's the actions, and student academic progress outcomes. And what we find, we test this conditional independence test on 20 different actions that advisors recorded systematically if they took in meetings. And we find that 5 interventions of the 20 are significant on this test. That is 2/3 of advisor interventions by volume. So that suggests that 2/3 of the interventions advisors took in the treatment arm of this experiment might have been expertly targeted to students. Since this is only a necessary condition of expertise and not sufficient, we also draw on really rich qualitative data from this the treatment arm of this trial to try and understand if advisors really were drawing on non-algorithmic contexts. So to do that, we take the data of, or the comments of meetings associated with the interventions that came up significant on our test, and we look for actual signs of non-algorithmic information being incorporated when advisors describe their decision-making for those interventions. So for example, for the intervention of recommending a schedule, we see advisors incorporating things like student health conditions that require courses to be in proximity, students or advisors customizing to try and motivate students who may not be motivated to stay in college, and taking into account sort of enrollment requirements for transfer to other institutions. And this is a pattern we see across significant interventions that advisors are incorporating non-algorithmic context. So to summarize, we create a framework to understand whether human expertise is present in use of algorithmic tools, and show that it is present in is present in this experiment treatment arm from both qualitative and quantitative lenses. And then one upshot of that, just returning to the motivation of scaling and capacity, is that if we want to see positive effects of these interventions scale up, we need to think about scaling human expertise in addition to algorithmic predictions. So thank you so much. I appreciate your attention. Yes, yeah, great question. So this was a past experiment, and primary analysis of the experiment found positive treatment effects, but didn't analyze any of the qualitative data that was collected or the advisor action data that was collected. So we were secondary analysis looking at that. Yeah, so the purpose of the experiment was to see whether the use of this advising protocol, drawing on early alerts, as well as intensive advising of students, would lead to positive outcomes on student enrollment and GPA.
Thanks for the talk, Kara. One question, like if you had to design a new experiment going forward, how was like the qualitative analysis of the comments? Would you do that again, or would there be other things you measure to try to like identify expertise a little bit more?
Yeah, that's a great question. I think definitely on the qualitative side, the comments were very helpful. I think maybe prompting advisors in certain ways to talk about their decision-making processes, because the comments were really just kind of open-ended. It didn't give particular instructions to advisors, would be very helpful. On the quantitative side, I think there's an interesting question of, is there stuff that we can do in order to try and actually identify the effect of non-algorithmic information? But it seems like a hard problem to me because experimentally controlling non-algorithmic information is difficult and might require like making the, like, doing it in a lab or making it like less realistic. So that's a question I'm thinking about and curious about. Yeah.
Okay, let's thank her again.